Is it rolling? Okay, are we taping? Is the red light on? Okay. We are gonna do a Hardy-Weinberg into chi-square analysis. What are you looking at? This is Joyce behind the camera here. Let's say we have a population of organisms, and I'm kind of drawing their genetic structure like this. This is the population. I'm going to make a few more organisms. Okay. Let's count the homozygous dominant individuals for this gene. There is 1, 2. Let's count the homozygous recessive ones. There is 1. 1? Am I wrong? 1. And heterozygous individuals, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. So that should be a total of 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Good. All right. Let's figure out the number of alleles. The A allele is, that's going to be 4 plus 10. There's 14 of those. And the recessive allele, there is 10, 11, 12 of those. I hope that makes sense to people. That would be out of, this would be out of 13 total organisms, and this would be out of 26 total alleles, right? So I could, I was about to say, where's my phone, my calculator? Can I use your calculator? Let's see if I can, it needs to fade, you need to do your
You just
thing.
put up and then that.
Beautiful. I've never had a phone beyond the 8 Plus, so I would not know how to do it. So 2 divided by 13 is, this is going to be p squared, right? So I'm just going to put that here. This is what, not expected, but what's observed. Q squared would be 1 out of 13, 0.07, and heterozygotes, that's 2pq, would be 10 out of 13. Whoops, let's try that again. 10 out of 13, that's 0.76. Frequency of the dominant allele, 14 divided by 26. So this is going to be P, that's 0.53, and Q is going to be, should be 0.47. Let's just make sure that 12 out of 26 is 0.46, but that's good enough. Okay, so this is all what we observe. I'm going to set up a little chi-square calculation to see if what we observe is what we would expect. Okay, so there are 3 categories of genotypes here. There's homozygous dominant, there's heterozygous, there's homozygous recessive. I'm doing my little a's differently now for some reason. Why am I doing little a's in 2 different ways? No one knows. No one knows. Observed. Remember, this should be count data on a chi-square. So this is 2, this is 1, this is 10. That is a total of 13. How do I get my observed?
Are you asking me?
This is tricky. Unless someone really directly teaches you what to do at this step, I think it's hard to guess what to do. What you are going to do if you have to do a Hardy-Weinberg / chi-square. Remember, I always tell you that the expected is usually the trickiest part. Sometimes it takes a little bit of common sense if it's not a Punnett square or Hardy-Weinberg, but if it's in the context of heredity or Hardy-Weinberg, you're probably going to do a Punnett square or a Hardy-Weinberg something to figure it out. So this is a Hardy-Weinberg one. What I am going to do is I'm going to take my observed allele frequencies. The ones I actually counted that I know are real, and I'm going to plug them in to the hypothetical Hardy-Weinberg equation, right? So I'm going to need my calculator again. Joyce taught me how to use an iPhone 10.
13.
13. Holy moly, wow, flexing on, excuse me,
No.
this is a no flex zone, so I'm gonna need you to take that back.
Okay.
Calculator. P squared, okay, 0.53 times 0.53 is, that is 0.28. 0.47 times 0.47, that is 0.22. 2PQ. 0.53 times 0.47 equals times 2 equals 0.49. Notice 2PQ is very often 0.59. So 0.49 I should say. All right. Oops, I still need my calculator. Here are my expected frequencies. Do frequencies go on a chi-square table? They do not. Let the record show Joyce correctly answered that question. Calculator, okay. How do I convert this to count data? Well, I multiply each frequency by my population size to get number of individuals. So 0.28 times 13. I would expect 3.6, I'm going to make that 4. 0.49 times population size, 13. 6.37, I'm going to make that 6. 0.22 times 13. 2.8, I'm going to make that 3. These are my expected frequencies. Now I'm going to do my chi-square. Observed minus expected. By the way, if Jimmy McHugh wants me to say this, if you have a scientific or graphing calculator and you know how to do a chi-square function on the calculator, you can do it. But I'm assuming not everyone's going to have that calculator, and I don't know how to do that. So if you have a chi-square button on your calculator and you know what you're doing, you can do that. But you're still going to have to do some biology to figure out your expected numbers. So just wanted to say that. Observed minus expected. This is -2. This is 4. This is -2. Observed minus expected squared. This is 4. This is 16. This is 4. Over expected. 4 divided by 4 is 1. 16 divided by 6, I don't know. 4 divided by 3, I think I know. But here we go again with Joyce's phone. 16 divided by 6 is 2.6. 2.66 actually. I like the hundreds place on these. 4 divided by 3, 1.33. What do I do when I have all the values from my columns, however many columns I have? I add them up. So 1 plus 2.6 plus 1.33, 1 plus 2.66 plus 1.33 equals 3.99. Right, that is my chi-square value. I compare the value to the degrees of freedom table. What's the number of degrees of freedom here? It's the number of categories minus 1. So the degrees of freedom, little d, big F, is going to be 2. And what is my critical value? I'm going to go to my formula sheet, and I'm going to say, okay, chi-square table, degrees of freedom 2. Critical value is 5.9. I'm using a p-value of 5. So, does my chi-square value, is that right? Yes, it is. Does my chi-square value exceed the critical value? No, it does not. This means I'm going to accept my null hypothesis. We never articulated that, but it's going to be there is no difference between observed and expected. So it turns out that this is actually, even though it doesn't match our expectations exactly, this is pretty much what we would expect. I think the reason why, I honestly, going into this, I tried to make there be, I'm gonna reveal, I tried to make there be way too many heterozygotes, so we could reject the null hypothesis, but I think I just didn't make enough organisms. There's such a small sample size here that our chi-square calculation is saying, you know what, you have a really small sample size, it's probably due to random chance that there are more heterozygotes than expected, and in fact, you should accept the null hypothesis that says there is no statistically significant difference between observed and expected. And that is the end of this video.